Learning Module Simulation Methods. Topic: Lognormal distribution and continuous compounding. An analyst records Balder Corp's daily share prices. August 1st close equals 74.20. August 2nd close equals 75.30. August 3rd close equals 73.60. August 4th close equals 78.10. Using continuously compounded return definition, the accumulated return from August 1st to August 4th is closest to A 5.25%, B 1.72%, C 5.12%. In contrast to log-normal distributions, normal distributions A. Allow both positive and negative values. B. Are always right-skewed. C. Are more suitable for modeling asset prices. An analyst chooses to model stock returns with a normal distribution and stock prices with a log-normal distribution. This is because A. Stock returns cannot be negative, while stock prices can. B. Stock returns can be negative, while stock prices cannot. C. Stock returns and prices are both bounded below by 0. If asset prices are assumed to follow a log-normal distribution, then which of the following is most likely true? The asset price can be either positive or negative. B. The asset price distribution will be symmetric around the mean. C. The asset price is bounded below by 0 and right-skewed. An analyst assumes that a stock's price follows a log-normal distribution. This implies that the stock's continuously compounded return is A. Uniformly distributed, B. Normally distributed, C. Right-skewed and bounded below by 0. An analyst is evaluating the distributional properties of a commodity price. She observes that the price cannot fall below 0 and that extreme positive price movements occur more frequently than extreme negative movements. Which of the following conclusions is most consistent with these observations? The commodity price is best modeled using a log-normal distribution because it is bounded below by 0 and exhibits positive skewness. B. The commodity price is best modeled using a normal distribution because it is symmetric. C. The commodity price is best modeled using a log-normal distribution because it is completely defined by its mean and variance. The accumulated continuously compounded return is the natural log of the price change, calculated as log of Pn divided by P start. Over multiple days, you sum the daily log returns. The accumulated continuously compounded return over multiple periods is the sum of the individual one-period returns. Normal distributions allow both positive and negative values, making them suitable for modeling returns. The incorrect options highlight that normal distributions are symmetric, not skewed, and unsuitable for asset prices, which cannot be negative. Normal distribution defined over negative infinity, positive infinity, symmetric, used for returns. Log-normal distribution defined over 0, positive infinity, right-skewed, used for prices. Returns can be negative while prices cannot. This is why returns are modeled with a normal distribution, defined over negative infinity to positive infinity, and prices are modeled with a log-normal distribution, bounded below by 0. The incorrect options reverse or misstate this logic. Normal distribution. Its range is negative infinity to positive infinity, making it a good approximation for returns because it allows for negative values. Log-normal distribution. Its range is 0 to positive infinity, making it the appropriate model for asset prices because they are non-negative and typically right-skewed. Log-normal distribution is defined only for values greater than 0, which matches the physical reality that asset prices cannot fall below 0. Additionally, its right-skewed, long right tail Shape accurately describes the asymmetric behavior of financial asset prices. Normal distribution. Suitable for returns because it is symmetric and defined from negative infinity to positive infinity, allowing for negative values. Lognormal distribution. Suitable for prices because it is defined from 0 to positive infinity, ensuring prices remain non-negative. Reciprocal relationship between the two distributions. A variable, price, is lognormal if its natural logarithm, return, is normally distributed. The mnemonic provided in the sources, the log is normalis, the direct key to identifying that log-normal prices imply normal returns. Domain and asset modeling. The alignment here is based on the mathematical bounds of each distribution. Normal distribution. It is defined over negative infinity to positive infinity, making it a good approximation for returns because returns can be negative. Log-normal distribution. It is defined over 0, positive infinity, making it the appropriate model for prices because asset prices are bounded below by 0 and cannot be negative. Asset prices are bounded below by 0, which matches the observation that the price cannot fall below 0. The observation of extreme positive movements refers to the log-normal distribution being skewed to the right, having a long right tail, positive skewness. Unlike the log-normal, a normal distribution is symmetric and permits negative values, making it inconsistent with the observed price behavior. If the natural logarithm of a variable, the return, is normally distributed, the variable itself, the price, follows a log-normal distribution. Because the distribution cannot spread below 0, as variance increases, the distribution's center is pushed to the right, which creates the positive skewness noted by the analyst. Topic: Monte Carlo simulation. A portfolio manager runs 10,000 Monte Carlo simulations to project a fund's one-year return distribution. The output is most useful for A. Understanding the range and likelihood of possible return outcomes under uncertainty. B. Identifying a single most likely return that will certainly occur. C. Eliminating the need for assumptions about probability distributions. Compared with analytical methods, a primary strength of Monte Carlo simulation for valuing securities is that it guarantees exact solutions to complex valuation problems. B. Can be applied when no closed-form analytical solution exists. C. Eliminates the need for assumptions about probability distributions. A major weakness of Monte Carlo simulation compared with analytical methods is that A. Monte Carlo simulation is limited to normally distributed inputs. B. Monte Carlo simulation cannot be applied to securities with embedded options. C. Monte Carlo simulation provides only statistical estimates rather than exact solutions. Monte Carlo simulation is most appropriately used to A. Eliminate the need for assumptions about probability distributions. B. Generate exact analytic formulas for valuing complex securities. C. Model uncertainty by producing many possible outcomes based on specified probability distributions. A disadvantage of Monte Carlo simulation compared with analytical methods is that it provides statistical estimates rather than exact solutions. B. Cannot be applied to securities with complex embedded options. C. Requires all inputs to follow a normal distribution. Monte Carlo simulation produces a distribution of possible outcomes based on assumed probability distributions. It shows the range and likelihood of returns under uncertainty, not a single guaranteed outcome. Option B is wrong because Monte Carlo does not predict certainties, and option C is wrong because it requires assumptions about distributions. Monte Carlo relies on assumed probability distributions, useful for risk and sensitivity analysis. Bootstrapping resamples observed data, does not require distributional assumptions. Use Monte Carlo when modeling uncertainty under assumed distributions. Use bootstrapping when distribution is unknown but historical data is available. Monte Carlo simulation is most useful when no closed-form analytical solution exists. It provides statistical estimates by simulating thousands of random scenarios, which makes it valuable for complex securities, with features that cannot be solved analytically. Option A is wrong because Monte Carlo does not guarantee exact solutions, and option C is wrong because it requires distributional assumptions. Analytical methods, exact solutions when formulas exist. Monte Carlo, statistical estimates, useful when closed-form solutions do not exist, requires assumed distributions. Bootstrapping, resampling observed data, avoids distributional assumptions. Use analytical methods when formulas exist. Use Monte Carlo when securities are too complex for closed-form solutions. Use bootstrapping when you want to rely on observed data without assuming distributions. Monte Carlo simulation provides only statistical estimates rather than exact solutions. It relies on repeated random sampling, so results are approximations. Analytical methods, when formulas exist, yield exact closed-form solutions. Option A is wrong because Monte Carlo is not limited to normal inputs, and option B is wrong because Monte Carlo is actually useful for embedded options, not excluded from them. Analytical methods, exact solutions, clarity, but limited to tractable models. Monte Carlo, statistical estimates, useful when no closed-form solution exists, requires assumed distributions and repeated trials. Use analytical methods when exact formulas exist. Use Monte Carlo when securities are too complex for closed-form solutions, but accept that results are estimates. Monte Carlo simulation models uncertainty by producing many possible outcomes based on specified probability distributions. It does not eliminate the need for assumptions. Option A is wrong. And does not generate exact analytic formulas. Option B is wrong. Its strength lies in simulating thousands of scenarios to show the range and likelihood of outcomes. Monte Carlo, statistical estimates, relies on assumed distributions, useful for modeling uncertainty and complex securities. Analytical methods, exact closed-form solutions, limited to tractable models. Bootstrapping, resampling observed data, avoids distributional assumptions. Use Monte Carlo when modeling uncertainty under assumed distributions. Use analytical methods when exact formulas exist. Use bootstrapping when distribution is unknown, but historical data is available. Monte Carlo simulation provides statistical estimates rather than exact solutions. It relies on repeated random sampling, so results are approximations. Analytical methods, when formulas exist, yield exact closed-form solutions. Option B is wrong because Monte Carlo is actually useful for complex embedded options. And option C is wrong because Monte Carlo is flexible and can use many different distributions, not just normal. Analytical methods, exact solutions, clarity, but limited to tractable models. Monte Carlo, statistical estimates, useful when no closed-form solution exists, requires assumed distributions and repeated trials. Use analytical methods when exact formulas exist. Use Monte Carlo when securities are too complex for closed-form solutions, but accept that results are approximations. Topic: Bootstrapping. Bootstrapping in simulation analysis is best described as A. Drawing repeated samples from a theoretical normal distribution. B. Drawing repeated samples with replacement from the observed data set. C. Drawing repeated samples without replacement from the observed data set. The primary advantage of bootstrapping in finance is that it requires strong parametric distributional assumptions about returns. B. Can be applied even when the underlying return distribution is unknown. C. Eliminates all sampling error in small data sets. Which of the following is most likely a limitation of bootstrapping in portfolio risk analysis? A. It cannot be applied when the number of observations is small. B. It may reproduce biases and patterns already present in the original sample. C. It requires knowledge of the exact theoretical distribution of asset returns. An analyst is considering using bootstrapping to estimate the distribution of portfolio returns. Which of the following concerns should the analyst most carefully evaluate before relying on the results? Whether bootstrapping assumes asset returns are normally distributed. B. Whether resampling will replicate biases or unusual patterns already present in the sample data. C. Whether bootstrapping eliminates estimation error when applied to small datasets. Bootstrapping means drawing repeated samples with replacement from the observed dataset. This allows variability and mimics population sampling without assuming a theoretical distribution. Option A is wrong because that describes Monte Carlo, using assumed distributions, and option C is wrong because sampling without replacement would only reshuffle data, not generate new variability. Monte Carlo relies on assumed probability distributions, generates random draws, useful for modeling uncertainty when distributions are known. Bootstrapping resamples observed data with replacement, avoids distributional assumptions, useful when distribution is unknown but historical data is available. Use Monte Carlo when you want to simulate outcomes under specified distributions. Use bootstrapping when you want to simulate outcomes directly from observed data without assuming a distribution. Bootstrapping's primary advantage is its ability to be applied even when the underlying return distribution is unknown. It resamples observed data with replacement, avoiding the need for parametric distributional assumptions. Option A is wrong because that describes Monte Carlo, which requires assumed distributions, and option C is wrong because bootstrapping does not eliminate sampling error. Small datasets still carry variability. Monte Carlo requires assumed probability distributions, useful when distributions are specified. Bootstrapping resamples observed data with replacement, useful when the true distribution is unknown or difficult to specify. Monte Carlo equals distribution-driven simulation. Bootstrapping equals data-driven resampling. Bootstrapping may reproduce biases and patterns already present in the original sample. Since it resamples observed data with replacement, any anomalies or structural issues in the dataset will be carried forward. Option A is wrong because bootstrapping can still be applied with small datasets, though results may be less reliable. And option C is wrong because bootstrapping does not require knowledge of theoretical distributions. That's Monte Carlo. Monte Carlo, assumption-driven, requires specified probability distributions. Bootstrapping, data-driven, resamples observed data with replacement, but replicates any bias in the data. Bootstrapping equals data-driven resampling, biases persist. Monte Carlo equals distribution-driven simulation, requires assumptions. Bootstrapping may reproduce biases or unusual patterns already present in the sample data. Since it resamples with replacement from the observed dataset, any anomalies or structural issues in the data will be carried forward. Option A is wrong because bootstrapping does not assume normality. That's Monte Carlo. And option C is wrong because bootstrapping does not eliminate estimation error. Small datasets still carry limitations.